Alright, one more time. We are in section 3.2 for Math 95. We're talking about functions, and so far we have defined the relation, domain, range, function. We've learned how to use the vertical line test for functions, and we've found the domain and the range of a function. In this last video, I want to talk about something called function notation, and it's something you're going to be using for the rest of your math life. So let's spend some time with that. Before we can talk about function notation, there's a little bit more vocabulary that we need. I want to talk about the independent variable and the dependent variable. The independent variable is a fancy name for your inputs. It goes with your x values. It's what you're plugging into your function. And so the dependent variable is going to be your outputs, or your y values. So we use function notation to show when y is a function of x, y is depending on x. And we use this very specific notation to tell me that y is a function. My relation is a function, only one output for each input. It has a lot more uses, but for now I just want to get used to working with it. We read this as f of x, and it's showing the dependence that y has on x. So I have a couple functions here, and I just want to translate them into function notation. So I'm actually going to drag this over here in this one here, and I'll write their function notation versions underneath them. For function notation, all we're doing is we're changing the name of y. So change the name of the dependent variable. So this one was y. I can't use y because y's already been used. We like f of x as function notation because f stands for function. So if I wanted to change this to function notation, I just change the y to f of x, and I keep the rest of the relation the same. I have an x squared plus 2x minus 3. I'm not committed to f of x. I could choose something else. So for this case, instead of having y, I could have g of x as our next favorite function, because we like to go alphabetical, f, then g. I've only changed the name of my dependent variable, y turned into g of x, and the rest of it stays the same. So if I ask you to translate something into function notation, just change the y into an f of x. That's all there is to it. So if I have these two functions, I can answer some questions about my functions. If I want to find f of negative 1, what that's telling me is that my x value for my function is the value that's inside these parentheses. So if I wanted to find f of negative 1, my first step is to copy my function down, but instead of an x, I'm going to put a set of parentheses. And then inside those parentheses, I'm going to place the x value that I'm interested in. And now it's an order of operations problem. Again, you can do this in your calculator. I'm going to do it in my head. Negative 1 squared is 1, times 3 is 3. Negative 1, that makes it plus 1, and a plus 2. So f of negative 1 is 6. This corresponds to the ordered pair, negative 1, 6. The input was negative 1, the output was 6. these two things mean the same thing. So if I were to find f of 2, I'm going to do 3 times 2 squared minus 2 plus 2. Order of operations says do the exponents first, so 2 squared is 4, times 3 is 12. And then I subtract 2 and add 2. These two make 0. I'm not even going to bother with that. I get f of 2 is 12. Meaning that when x is 2, y is 12. It's like 121. Let me make that a little bit cuter. I could look at something like f of 2a, which is a little weird. So I'm going to just do what I did before, 3, parentheses, my x value is a 2a now, squared, minus 2a plus 2. Give myself a little bit more room to work. 2a squared, that 2 distributes down, making this a 4 and an a squared. So this will be 3 times 4a squared minus 2a plus 2. I dropped these parentheses because they're not really needed right there. Now this 3 and this 4 multiply, making this a 12a squared minus 2a plus 2. So f of 2a equals this entire expression. I didn't get a single value out. Sometimes you won't. That's okay. There's not really an ordered pair that can correspond with this unless I plug an a value in, so I won't do that stuff. We could try the same thing with g. We have a different function. G of x is 4x plus 5. I want to find g of negative 5. I can just put a dotted line here so we don't get them confused. G of negative 5 will look like 4 times negative 5 plus 5. That looks like an and symbol. Let me try that again. Plus 5. 4 times negative 5 is negative 20. Plus 5, I get g of negative 5 is negative 15. And I freak out the whiteboard. There we go. Same thing with g of 0. Ooh, I don't want you to grab that. Sorry, let me try that again. This corresponds to the order pair negative 5, negative 15. And if I wanted to do g of 0, 4 times 0 plus 5, I get that g of 0 is 5, which corresponds to the order pair 0, 5. Function notation is a very convenient way of asking to plug in various x values or input values into your function. We like to use it to ask for specific values. You could also do this from a graph. Here I have graphs of two different functions. I've got a g of x in orange and an f of x in green. So f of x corresponds to green. Let me just underline it so we can see what's going on. And g of x corresponds to orange, so I'll just call it red, so it's a little easier to identify which is which. Now, from the graph, when I say find f of 2, remember, I'm looking for when 2 is my input. So if 2 is my input, that's not the color I wanted. If 2 is my input, it's the first piece of my ordered pair. So when 2 is my input, that's here on my graph. This is where 2 is my input. So this touches my green line all the way down here. This right here is f of 2. And its corresponding output value is 1, 2, 3, 4, 5, 7, 8. It's a negative 8. that gives me the ordered pair 2, -8. But when I ask the second question, f of x equals 2, what this is asking is, what is my x value when my y value is 2? What goes right here in the front of my ordered pair? So I need to look at when my output is 2, which is right here, and then find what my input value is, and that's here at -2. So f of x equals -2 tells me that my x value is -2. This notation asks for the the x value, excuse me. This notation asks for the y value. Let's try that with our other function, our g function. So I'm asking for g of 3. In other words, what's the value of my orange function when x is 3? So to remind myself, I'm going to put a 3 here at the front of my ordered pair. I could go here to my x-axis and say, okay, this is where my x value is 3, and well, look at that, I am right there at 0. So when I plug 3 in to my g function, I get out as 0, because that's the y value when x is 3. So this is the point 3, 0. But how about when g of x equals 3? In other words, 3 is my output value. Let me do this in a different color. What have I not used yet? Don't want to use yellow. Let me grab a new color. Let's do a purplish, orangish thing. So, g of x is 3. That's going to be here at this dotted line where my y value equals 3. And if you look, that's going to correspond to 2 different x values. This is a little crowded over here. I apologize for that. So, g of x is 3 at 2 different x values. It happens over at, let's see, 1, 2, 3, 4, 5, 6, -6, 3, and looks like at 4, 3. So I have 2 x values for when the output value is that 3. Remember, that's not a problem. My inputs need to be unique. My outputs do not. Let me clean up my graph just a little bit before I go on to the next slide. I wanted to... I'll leave it. It's fine. Okay. One more slide to go. I have an application problem. We sometimes like to use function notation in an application problem. So here's my goofy application problem for today. We're vacationing on Mars because we know that's going to be possible in our lifetimes. Yes, I'm joking. We're shooting a firework straight up in the air, and this is the velocity. So for every second that it travels, it's going 100 meters in the air. And this would not be possible on Earth, but it's possible on Mars because, well, gravity is less there. I'm giving you the equation of motion, but I need to define my variables so I know what it is I'm talking about. So this models the height of our sparkler as a function of the number of seconds it's in the air. So this is different than what we talked about in class for how to define variables. If you see the phrase as a function of, that's telling you that the piece right before it is the output, and the piece after it is the input. You can also think of that the height of the sparkler is dependent on the number of seconds it's in the air, which makes the second piece the independent variable, the first piece the dependent variable. That will take a little bit of practice. You might want to replay this part of the video a couple of times just to be clearer about it. So if I were to label my variables. I've already been given the names. So t is my input. And that's going to be the number of seconds the sparkler's in the air. And then the other variable I was given, x of t, that's my output. And that will be the height of the sparkler in meters. I know it's meters because I have meters here. I don't explicitly say that. So now I'm asked to find x of 10 and x of 15. So if I use my function notation, x of 10 is going to be negative 5 times that 10 squared plus 100 times 10. I'm looking right here. I can do a little mental math. I know that 10 squared is 100 times negative 5 gives me negative 500. And then 100 times 10 is 1,000. So x of 10, actually 1,000, excuse me, is 500. Now, I have to be careful. How is this measured? This is my output. This is my input. So this is going to be meters, which means the sparkler was 500 meters in the air after 10 seconds. That's what it means. When I say interpret what they mean, you need to put them back in the context of the problem. So include units on them. Let's do the other one. X of 15, set it up the same way. Negative 5 times 15 squared plus 100 times 15. Now, 15 squared is going to be 225. 100 times 15 is 1,500. I'm going to do this in my head. You can use your calculator. I'm just going to think this through really quick. 200 times 5 is 1,000. 25 times 5 is 125. So this is negative 1,125 plus 1,500. If I do that in my head, it's 500 minus 125 is 375. Let me erase this last one. Did I say 375? So now I've forgotten. Let me pause while I calculate this. Okay, so you can see I pulled up my TI calculator. I had to find it, and I get 375. So I get a let me use a marker. 375 meters. So x of 15 is 375 meters. Let me drag this down for a minute. Get my pen back. So at 15 seconds in the air, the sparkler is 375 meters high. You technically need to answer all application problems with a complete sentence. So part A is not complete. I'm just going to say it. It is 500 meters high at 10 seconds. That's all I need to show. one last piece of this and then I'll let you go. If your Martian dog, called a Mog, it's true, was going to fetch your sparkler as it hit the ground, how long would he have to wait for it? Now, we're not going to solve this right now. We could, but I just want to set it up. So if I want to find out when the sparkler is going to hit the ground, that was weird. If I want to know when the sparkler is going to hit the ground, I need to know what the height of the sparkler is when it hits the ground. Because what I'm asked for is how long he would have to wait for it. I'm looking for a t equals. I do a little bit of thinking. X of t was the height of the sparkler, so how high it is above the ground. When I'm at the ground, x of t has to equal 0, because it's at the ground. That's what that means, and that's going to be a trick you'll see in your homework. So I'm going to set up the equation 0 equals negative 5t squared plus 100t. Now, if you just came from Math 65, you have some strategies for solving this. This class is going to develop even more strategies for solving a quadratic equation. We are not going to solve this right now. But we will develop strategies for solving this later on in the class. With that, you should have everything you need to complete the section 3-2 homework. All right, I'll see you in class.